Close your eyes. Count to 10. 1, 2, 3. What are you counting? Are you counting the ticks of a distant clock hanging on a damp wall? Or are you counting the slow, electrochemical firing of synapses in the dark theatre of your own skull? We have a habit, we humans, of treating time like a river. We imagine it flows. We imagine it carries us from a past we cannot touch toward a future we cannot see. But tonight, we are going to dismantle the river. We are going to drain the clock of its gears. We are going to ask the universe a question it does not know how to answer. A question that has driven physicists to the edge of madness and philosophers to the bottom of a glass. The question is this: if time is not a river, if time is not a ticking gear, if time is not a dimension you can walk along, then what is it made of? This is part 1 of The Fabric of the Now, a descent into the quantum basement of reality, a place where the past is a ghost, the future is a probability cloud, and the present is a razor's edge that does not actually exist. Let your eyelids grow heavy. Let the drone of the cosmos fill your ears. We are about to unmake the clock. Before we dive into the quantum foam, we must first confront the ghost that haunts our every waking moment, the classical idea of time. Sir Isaac Newton, the man who saw an apple fall and saw the moon, believed time was absolute. He called it true mathematical time, flowing equably without relation to anything external. For Newton, time was a giant, invisible stage. The universe was a play, and time was the wooden floorboards beneath the actors' feet. Whether the actors were dancing or dying, the floorboards remained unchanged. But Newton's time was always a lie. It was a useful lie. It helped us build bridges and shoot rockets. But it was a lie nonetheless, because time, as we experience it, is sticky. It is emotional. It bends. An hour spent waiting for a phone call can feel like a geological epoch. An hour spent laughing with a friend dissolves in a breath. Then came Einstein. He shattered the wooden stage. Einstein showed us that time is elastic. It stretches with speed. It warps with gravity. He threw the clock out of the absolute room and made it a resident of the physical universe. He said, "Time is what a clock measures." And a clock, he reminded us, is just a thing. A lump of metal and quartz. If a thing can be warped, the time it measures is warped too. He called this spacetime, a four-dimensional fabric, a fabric that can ripple, tear, and twist. But Einstein left one stone unturned. He made time flexible, yes, he made it relative, but he left it as a continuum, a smooth, unbroken line. He never asked, what is the smallest stitch in this fabric? He never asked, does time come in pieces? That is where we begin our slow, sleepy descent. We leave the macroscopic world of trains and falling apples. We leave the world where a second is a second. We are going to shrink. We are going to shrink past the microscopic, past the cellular, past the molecular. We are going to drop into the realm of the quantum, where the rules of the universe are written in probabilities, not certainties, where a particle can be in two places at once, and where time forgets how to behave. Let us look at the great map of the quantum realm. The Schrödinger equation. It is the engine that drives the quantum world. It looks like this. I, the negative, the proportion of psi over the proportion of t equals h hat psi. Beautiful, isn't it? It looks complicated, but at its heart, it has a very special feature. Do you see the little t in the corner? The t stands for time. But here is the quantum secret. In this equation, time is not a property of the particle. Time is a parameter. It is a label. It is like the page number in a book. The particle's wave function, psi, evolves as a function of time. Time is the stage, just like Newton said. But now, the stage is just a parameter in a mathematical machine. You put in a time, you get out a state of the particle. It's deterministic. It is clockwork, but with ghosts. But watch what happens when you look at it. That cloud collapses. The wave function snaps into a single point. This is the measurement problem. And this is where time gets its first deep wound. According to the Schrödinger equation, the evolution of a particle is smooth, continuous, and reversible. You can run the film backward. There is no arrow of time in the quantum realm. Yet, when you measure it, when you look at it, the system jumps. It collapses. It goes from a many to a one. Where does that collapse live in time? Does it take time to collapse? The great physicist, John von Neumann, proposed that the collapse happens in the consciousness of the observer. Others proposed it happens when a particle interacts with a large classical environment. But the unsettling truth is this. The fundamental equation of quantum mechanics is timeless in one direction. It is symmetric. It does not care if you go forward or backward. The irreversibility, the feeling that time is a one-way street, only creeps in when we open our eyes. So, time in the quantum world does not flow. The wave function merely rotates in a high-dimensional space. The t is just a coordinate. If you were a photon, a particle of light, traveling at the speed of light, you would experience no time at all. You would be born and die in the same instant, separated by billions of light years. Are you still there? Let the weight of that sink in. The thing you call your life, this long, dragging narrative of memory and anxiety, is, from the quantum perspective, just a series of correlations between a label T and a mathematical state. But the deeper we dig, the worse it gets. Because if time is just a label, a parameter, then what happens when we try to combine quantum mechanics with the fabric of the universe itself? That is the problem of quantum gravity, and that is where time dies. There is an equation. It is the nightmare of modern physics. It is the equation that unites the very large, gravity, with the very small, quantum. It is called the Wheeler-DeWitt equation, and it is a terrifyingly simple little thing. It looks like this. H hat psi equals 0. It looks innocent. It just says that the Hamiltonian operator, the mathematical tool that measures the total energy of the universe, acting on the wave function of the universe, gives you 0. Nothing. Zilch. The energy of the entire universe cancels out to exactly nothing. But look closer. Where is the t? Do you see it? The variable for time is gone. It has vanished. In the Wheeler-DeWitt equation, there is no time parameter. It is an equation of complete stasis. The universe, at its most fundamental quantum gravitational level, does not evolve. It simply is. It is a frozen block of isness. This is the problem of time. It is the single greatest headache in theoretical physics. We live in a universe where galaxies spin, people age, and empires crumble. Yet, the equation that best describes the quantum state of the entire universe suggests that nothing ever happens. It suggests that the universe is a frozen hologram, a static crystal of light and gravity, utterly timeless. How do we get from this frozen block to the ticking of the clock in your study? How do we get from a universe that has no time to a human being who cannot stop time? You might feel a knot in your stomach, the vertigo of the abyss. Do not fight it. Let the stillness wash over you. Because to solve this paradox, we must do something radical. We must abandon the idea that time is a fundamental building block of reality. We must look at time as an emergent property. like heat. Heat is not a fundamental thing. It is just the average kinetic energy of trillions of atoms jiggling. Similarly, time might not be a fundamental thing. It might just be the jiggle of quantum entanglement. This is the climax of our first descent. In 1983, two physicists, Don Page and William Wouters, came up with a solution so beautiful it makes you want to weep. They said, "Forget the universal clock. There is no cosmic timekeeper. Instead, time is relational. It exists between things." They proposed a model of the universe where the whole thing is in a pure, timeless quantum state. But inside this universe, there is a subsystem, a clock. This clock becomes entangled with the rest of the universe. The clock doesn't measure the flow of an external river. The clock measures its own internal correlations with the rest of the cosmos. Imagine you are holding a single photon, just one, and I am holding another. We send these photons into a crystal and they become entangled. They share a single quantum state. Now, if you measure your photon, your result is random. But if I measure my photon a moment later, relative to my wristwatch, our results will be correlated. That correlation, that link of information between you and me, is the tick of a clock. As the universe grows and more particles become entangled, the correlation network grows denser. This dense web of quantum connections gives rise to the illusion of a smooth, flowing time for the macroscopic objects embedded within it. For a large object, like a human, there are quadrillions of entanglements. The ever so slight increase in the entropy of this network of correlations gives us the sense of a past, a present, and a future. Time, in this view, is not a dimension. It is a degree of freedom. It is the measure of how much one part of the universe knows about another part. But here is the punchline. If you were a hypothetical observer located outside the universe, looking in, you would see absolutely nothing happening. The entire timeline of humanity, from the building of the pyramids to the dissolution of the sun, would look like a single, unchanging, frozen sculpture, a block of space-time. But because we are inside the universe, because we are entangled with the things around us, we experience the unfolding of those correlations as seconds, minutes, and years. Let me say that again, softly, so you can truly feel it. The passage of time is a symptom of our ignorance. We do not see the universe as it truly is, a four-dimensional, static crystal. We only see a slice of it. We see a projection. And because we are limited to this projection, we mistake the sequential unraveling of quantum correlations for the flow of a river. So, what is time made of? If we follow Page and Wouters, time is made of entanglement. It is made of the invisible threads that tie you to this planet, to this star, to the cosmic microwave background radiation left over from the Big Bang. You are a walking, breathing clock, measuring the universe against your own internal quantum state. But entanglement is not the only ingredient. To build time, you need structure, you need symmetry, and this is where the strangest creature in the quantum zoo enters our story, the time crystal. In 2012, the Nobel laureate Frank Wilczek began thinking about the nature of time in crystals. In a normal crystal, like a diamond, the atoms are arranged in a repeating pattern in space. This breaks the symmetry of space. If you move a diamond a tiny distance, it looks different. That's how you know it's a crystal. Wilczek asked, could we build a crystal that breaks the symmetry of time? A system that has a repeating pattern in time, even in its absolute lowest energy state, its ground state. Imagine a ring of atoms, constantly spinning, but never losing energy. A perpetual motion machine, but not a fraud. A time crystal is a system where the atoms rotate, oscillate, or flip at a specific, regular frequency. It is a state of matter that moves forever, without any energy being added to it. For a long time, physicists thought this was impossible. In the ground state, the state of minimum energy, everything is supposed to be still. But then, in 2016, researchers at the University of Maryland built one. They took a chain of ytterbium ions and zapped them with lasers. They found that the ions spontaneously began flipping at twice the frequency of the laser pulses. The system had locked itself into a repetitive cycle in time. What does this mean for the fabric of time? It means that time is not just an empty stage. It is a structural property. In a time crystal, time becomes material. It becomes a rhythm. It becomes a beat. If entanglement gives us the arrow of time, the time crystal gives us the quantum of time. It suggests that time, at its absolute base, might have a granularity. Perhaps the universe is not a smooth flowing river, but a sequence of discrete, resonant ticks. A time crystal is a clock that ticks forever, without a battery, without a drive. It is time pulled out of the continuum and solidified into matter. So, we have gathered our clues. From the dead parameters of Schrödinger, to the frozen tomb of Wheeler DeWitt, to the relational entanglement of Page and Wouters, and finally to the solid, ticking rhythm of the time crystal. What are we to make of this? The answer, if we are brave enough to accept it, is that time is not a thing in itself. It is a relationship. It is the way the universe handles information. It is the rate at which forgotten information becomes inaccessible. It is the beat of a quantum drum. We began this journey asking a simple question. What is time made of? And we have arrived at a paradox. We have found that time is made of the very thing that denies its existence. It is made of quantum correlations that vanish when we look for them. It is made of a frozen equation that forbids motion. It is made of a crystal that moves without moving. The physicist Carlo Rovelli once said, "Time is ignorance." We feel time because we do not know the entire state of the universe. If we knew the position and velocity of every single particle in existence, the future would be as clear as the past. The mystery would vanish, and with the mystery, the flow of time would vanish too. We live in the present. But the present is a thin membrane, infinitely thin, between the memory of a past that is gone and the expectation of a future that does not yet exist. The quantum world tells us that the membrane is not real. It is a statistical fluke, a beautiful, dizzying hallucination conjured by a billion entangled particles. As we close this first chapter of our descent, I invite you to listen to the silence. Listen to the hum of your own blood. Listen to the rhythm of your breath. That rhythm is time. It is not a thing you are traveling through. It is a thing you are doing. You are a time crystal. You are a temporal structure. You are a slow, complex unfolding of quantum information, temporary and magnificent. In part 2, we will go deeper. We will ask the terrifying question, if time is made of entanglement, does time exist when you are not looking at it? We will explore the quantum eraser, the delayed choice experiment, and the possibility that the past is actively being created by the present. We will cross the event horizon of a black hole, where time and space swap places, and we will meet the ultimate fate of all clocks. But for now, let the fabric of the now wrap around you like a heavy blanket. Let the ticking stop. Let the universe rest in its frozen state. Sleep now. Welcome back. If you are still awake, if your eyes have not yet closed under the weight of what we have already uncovered, then you are braver than most. In part 1, we dismantled the clock. We watched time dissolve from a flowing river into a frozen block. We saw the Wheeler DeWitt equation erase the variable t from the universe, leaving behind a static crystal of pure existence. we learned that time, in its deepest quantum description, is not a fundamental ingredient of reality. It is an emergent property, a side effect, a ghost born from the entanglement of a billion particles. But we left a door half open, a question hanging in the darkness like a half-remembered dream. If the universe is truly frozen, if all moments, past, present, and future, exist simultaneously in that four-dimensional block, then why do you remember yesterday and not tomorrow? Why does your memory point stubbornly toward the past, like a compass needle locked onto a magnetic pole? Why does the future remain opaque, veiled, while the past feels solid, concrete, real? Tonight, we cross that threshold. We are going to ask the terrifying question: does the past even exist when you are not looking at it? And worse, can the present reach back and rewrite what has already happened? We are about to enter the quantum laboratory. We are about to perform experiments that shatter our most basic intuitions about causality. And we are going to cross the event horizon of a black hole, where time and space trade places, and where the very concept of before and after loses all meaning. Let the darkness deepen. Let your breathing slow. We are going deeper still. The year is 1978. A physicist named John Archibald Wheeler is sitting in a darkened room thinking about light. Wheeler is a giant. He gave us the term black hole. He worked with Einstein, and now he is about to propose something that will make your stomach turn. He calls it the delayed choice experiment. Imagine a single photon, a particle of light. We send it on a journey. We place a beam splitter in its path, a half-silvered mirror that either reflects the photon or lets it pass through with equal probability. If we put detectors at the two possible exits, we find that the photon behaves like a particle. It takes one path or the other. Click. One detector fires. But if we remove the detectors and instead place a second beam splitter that recombines the two paths, something strange happens. The photon behaves like a wave. It interferes with itself. It takes both paths simultaneously, creating a pattern of light and dark fringes on a screen. So far, this is standard quantum mechanics. The photon behaves as a particle when we look at which path it took, and as a wave when we don't. But Wheeler asks a more devious question. What if we wait until the photon has already passed the first beam splitter, already committed to its journey, and then decide whether to insert the second beam splitter? What if we make the choice after the photon has already traveled most of the distance? Here is the nightmare. The photon's journey might have taken 1 billion years. It might have come from a distant quasar, traveling across the cosmos. And only at the very last moment, here on Earth, do we decide whether to place that second beam splitter or not. If we place it, the photon shows wave-like behavior, as if it took both paths all along. If we remove it, the photon shows particle-like behavior, as if it chose a single path. The decision we make now, in the present, determines what the photon did billions of years ago. Let that land. Let it settle. The past is not fixed. It is not a set of events that have already happened, already written in stone. The past is a probability cloud, a haze of possibilities that only crystallizes into a single history when a measurement is made. And that measurement can happen after the event supposedly occurred. Wheeler himself said it beautifully, with a poet's chill. We are participators in bringing into being not only the near and here, but the far away and long ago. We are not passive observers watching a film that has already been shot. We are active co-creators, reaching back through time, shaping the very history we think we remember. This is not science fiction. This has been tested in laboratories. The quantum eraser experiments of the 1990s and 2000s confirmed Wheeler's nightmare. They showed that by manipulating the information we have about a particle's path, we can retroactively determine whether it behaved as a wave or a particle. The past is, in a very real sense, a function of the present. So, what does this mean for time? It means that time is not a one-way street from a fixed past to an unknown future. It means that the future and the past are entangled. They are locked in a quantum embrace where the active observation in the present reaches backward and forward simultaneously. The block universe is not a static sculpture. It is a living crystal where every measurement reshapes the entire structure. But if that is true, then memory becomes something else entirely. Memory is not a recording of what happened. Memory is a correlation, a quantum link between your present brain state and a past event that only became real when it was first observed. You remember yesterday because your brain is entangled with a specific version of yesterday. But that version of yesterday only exists because someone, somewhere, looked at it. This brings us to a figure who haunts the margins of physics, a name that makes some scientists uncomfortable. Eugene Wigner, a Nobel laureate, a giant of quantum theory, and a man who believed that consciousness is the final observer. Wigner proposed a thought experiment. He imagined a friend inside a sealed laboratory, performing a quantum measurement. Outside, Wigner watches. For Wigner, the entire laboratory, including his friend, is in a superposition. The friend has measured the particle, so the friend's wave function has collapsed from the friend's perspective. But from Wigner's perspective, the friend is still in a superposition of having seen two different outcomes. Wigner asks, at what point does the wave function truly collapse? At the moment the friend looks at the apparatus, or at the moment Wigner opens the door and asks the friend what they saw? This is the Wigner's friend paradox, and it has recently been tested in real experiments using entangled photons to simulate the friend. The results confirm that different observers can have different, equally valid accounts of what happened. There is no single objective timeline. There are only perspectives. If time is relational, as Page and Wouters argued, then Wigner's friend takes that idea to its logical extreme. Time is not just relational between particles. Time is relational between observers. Your now is not my now. Your past is not my past. The universe does not have a single clock. It has a billion clocks, each ticking at its own rate, each entangled with a different slice of the cosmic wave function. You are beginning to feel it now, aren't you? The vertigo. The ground beneath your feet is dissolving. The solid foundation of what happened is becoming a shifting sand of quantum correlations. But we have not yet reached the deepest abyss. We have not yet spoken of the place where time not only bends or retroactively changes. We have not yet spoken of the place where time dies completely. We are going to the black hole. Imagine a star, a massive star, many times larger than our sun. It burns for millions of years, fusing hydrogen into helium, fighting against gravity. But eventually, the fuel runs out. The core collapses. The outer layers explode in a supernova, scattering stardust across the cosmos. And what remains is a point of infinite density, a singularity, a gravitational trap so deep that not even light can escape. This is a black hole. And at its edge, at the event horizon, time does something impossible. According to Einstein's equations, as you approach the event horizon, time slows down relative to a distant observer. If you were to watch a friend fall into a black hole, you would see them slow down, inch by inch, never quite crossing the horizon. Their clock would tick slower and slower, their image reddening, fading, freezing in time. You would watch them forever, suspended at the edge of eternity. But from the perspective of your falling friend, they cross the horizon in a matter of moments. They feel nothing unusual. They simply pass through. And then something stranger happens. Inside the event horizon, space and time swap places. The singularity, which was a point in space, becomes a moment in the future. You cannot avoid it. No matter how much you fire your rockets, the singularity lies ahead of you in time. The radial direction, the path toward the center, becomes temporal. You cannot turn back, because turning back would be like reversing time itself. Let me say that again, slowly, so it can sink into the quiet of your mind. Inside a black hole, time is not a dimension you move through. Time is a destination. It is a wall you are rushing toward. Your future is literally a place. And that place is the end of everything. Hawking later showed that black holes are not eternal. They evaporate. They emit radiation, slowly, over unimaginable eons, and eventually they disappear. But in doing so, they create a paradox. The information about everything that fell into the black hole, the books, the spaceships, the photons, the memories, seems to be destroyed when the black hole evaporates. But quantum mechanics says information cannot be destroyed. It can only be scrambled. This is the black hole information paradox. And the resolution, many physicists now believe, lies in the nature of time itself. If time is emergent from entanglement, then the information of the falling matter is not lost. It is encoded in the correlations between the Hawking radiation particles that escape the black hole. The information is spread across the quantum web, distributed in time. The past of the falling object is preserved, but it is preserved in a way that is non-local, scattered across the fabric of the universe. The black hole is not a destroyer of time. It is a weaver of time. It takes the smooth fabric and knots it into something deeply tangled. Now we must ask ourselves, what is the now? What is this thin membrane of presentness that we all inhabit? Some philosophers call it the specious present. It is the window of time we perceive as immediate. For humans, that window is about 3 seconds. 3 seconds of consciousness strung together, giving us the feeling of a continuous flow. But quantum mechanics suggests that the specious present is not a fundamental property of reality. It is a computational constraint. Your brain is a biological machine, processing quantum information through a dense network of neurons. To make sense of the world, your brain must construct a narrative. It takes the entangled correlations of the past, the sensory data of the present, and the predicted probabilities of the future, and weaves them into a coherent story. That story is what you call your life. But the story is always a simplification. It is a projection. Just as a 2-dimensional shadow of a 3-dimensional object loses information about depth, your 3-dimensional experience of time loses information about the true 4-dimensional block universe. You experience time as flowing because your brain is not capable of perceiving the whole crystal at once. You are a slow reader, trying to understand a book that is already complete. The physicist David Deutsch once said that the entire universe is a quantum computer, constantly processing information. But it does not process information in asterisk time. It processes information through time. The computation is the time. There is no external clock. There is only the computation itself. So, what is time made of, ultimately? We have seen that it is not made of seconds or minutes. Those are human inventions. We have seen that it is not made of a fundamental t variable in the equations of physics. That variable is a convenient fiction. We have seen that it is made of entanglement, of correlations between subsystems. We have seen that it is made of observer-dependent perspectives, collapsing wave functions, retroactive choices. But there is one more ingredient, one more layer to peel back. In recent years, physicists have been exploring the idea that time might be made of ignorance. Not in a poetic sense, but in a strict thermodynamic sense. The entropy of the universe increases. That is the only thing that gives us an arrow of time. But entropy is a measure of what we do not know. If we knew the exact microstate of every single particle in the universe, entropy would be zero. And without entropy, there would be no arrow. There would be no distinction between past and future. So, time is made of what we do not know. Time is made of the information that is hidden from us. As the universe expands, as quantum correlations spread and decohere, information leaks out of our local systems and into the environment. That leaked information is lost forever. We cannot recover it. That loss is what we experience as time passing. The past is the information we have lost. The future is the information we have yet to gain. The present is the razor-thin line where information is being exchanged, where correlations are being formed and broken. You are not moving through time. You are losing information, constantly, irreversibly. And that loss is what gives you the feeling that something is happening. This is the deepest truth we have uncovered tonight. Time is not a thing. It is a process of forgetting, a process of decoherence, a process of becoming more and more ignorant about the exact state of the universe. But even as we forget, we remember. Memory is the scar left by the loss. It is the fossil of a correlation that once existed. You remember your first kiss, not because the moment is still out there in the universe, but because your brain is still entangled with the configuration of particles that existed at that moment. That entanglement has degraded, of course. It has decohered, but the shadow remains. That shadow is memory. That shadow is what gives you the illusion of a past. Let us now look at the biggest question of all. If time is made of entanglement and ignorance, if the past is a function of the present, if black holes knot time into bizarre topologies, if observers create their own timelines, then what is left of the universe when no one is looking? This is not a philosophical question. It is a physical one. In quantum mechanics, an unobserved system is a superposition. It exists in all possible states simultaneously. The universe, before any observer appeared, was a pure quantum state. It was a wave function, evolving according to Schrödinger, timeless and directionless. Then, somewhere, something began to observe. Or perhaps, observation is just interaction, the entanglement of one subsystem with another. The universe observed itself, particles entangled with particles, atoms with atoms, stars with stars. And in that self-observation, time was born. Time is not a property of the universe when it is alone. Time is a property of the universe when it is looking at itself. You are the universe looking at itself. Your eyes are the universe's eyes. Your consciousness is the universe's consciousness, complex and localized, experiencing a tiny sliver of its own enormous wave function. You are the part that is aware of the part. And because you are aware, you experience time. But without you, without any observer, the universe would return to its frozen state. It would be a block of crystal, radiant and still, with no before and no after. This is what some physicists call the participatory anthropic principle. The universe requires observers to exist, in a certain sense. Not to exist physically, but to exist temporally, to have a history, to have a narrative. Without observers, there is no story. There is only the undifferentiated quantum foam. So, we have arrived at the end of our second descent. Let us gather what we have found. We found that the past is not fixed. It is a retroactive crystallization. We found that observers create their own timelines. We found that black holes are the graveyards of causality, where time becomes space and space becomes time. We found that time is the rate at which information is lost. And we found that without awareness, without an observer, time dissolves back into the quantum abyss. But there is one more thing, one more whisper from the darkness. If time is made of entanglement, and entanglement is the fundamental web of the universe, then you are not just a clock. You are a node in that web. Every person you have ever met, every star you have ever seen, every atom in your body, all of them are entangled with you. Your past is not your own. Your past is shared. It is distributed across the billions of particles that have interacted with you over the course of your life. When you die, what happens to your time? Does it vanish, or does it continue, encoded in the correlations that you left behind? In a very real physical sense, you do not cease to exist when your heart stops. You simply decohere. Your information spreads into the environment. The entropy of the universe increases a tiny bit, and the rhythm of your existence becomes part of the cosmic background noise. You become timeless. Tonight, we have walked to the edge of the abyss. We have looked into the quantum well and seen our own reflection staring back at us. The answer to the question, what is time made of, is the most humbling answer of all. Time is made of us. It is made of our ignorance, our limitations, our need to process the world in a linear sequence. It is made of the web of entanglement that connects us to everything that was and everything that will be. It is the shadow cast by a universe that is too vast and too complex for us to comprehend all at once. Close your eyes again. Feel your breath. That is time. Feel your heartbeat. That is time. Feel the slow, inevitable drift of your thoughts from one moment to the next. That is time. But know this, now, as you drift towards sleep. That flow is an illusion, a beautiful, necessary, profound illusion. The truth is that you are already at the beginning and the end, simultaneously. You are a four-dimensional object, stretched across the cosmos, touching the Big Bang and the heat death of the universe in the same eternal instant. You are not moving through time, you are time, moving through yourself. In part 3, if you are willing to descend even further, we will ask the impossible. We will ask, can we travel through time? Not in the science fiction sense of flying a machine into the past, but in the quantum sense, can we change the correlations of our own history? Can we untangle the web and reweave it? Can we, like Wheeler's photon, reach back and choose our own past? But that is a journey for another night. For now, let the silence swallow you. Let the frozen universe hold you in its crystal embrace. Let the entanglement of a trillion particles sing you to sleep. You are the clock, you are the time, and you are, finally, at rest. Sleep now.
Welcome back. If you have made it this far, if you have followed us through the vanishing present and into the abyss of the observer, then you have already surrendered something. You have surrendered the comfortable fiction of a clock that ticks uniformly. You have surrendered the solid ground of a past that is fixed and finished. You have stood at the event horizon and watched time and space swap places. And now we arrive at the final threshold, the question that has haunted physicists and poets alike since the birth of quantum theory. Asterisk. Can we change the past? Not in the crude science fiction sense. No flying machines, no plutonium-powered DeLoreans, no paradoxes involving accidental grandparents. We are not talking about macroscopic time travel. We are talking about something far stranger, far more subtle, and far more real. We are talking about the quantum possibility of reaching back through the correlations of the universe and rewriting the history of a single photon, a single bit of information, a single memory? Can the present reach into the past and choose a different path? Tonight, we are going to answer that question, and the answer will not comfort you. It will not give you a machine to fix your regrets, but it will show you that the universe is far more fluid, far more forgiving, and far more terrifying than you ever imagined. Let your eyes grow heavy. Let your thoughts slow to a crawl. We are about to unmake causality itself. To understand how we might change the past, we must first understand the strangest interpretation of quantum mechanics. It is an interpretation so bizarre that even its creators hesitated to fully embrace it. It is called retrocausality. The idea is simple, at least in its basic form. In standard quantum mechanics, the state of a system at a future time depends on its state at a past time. That is forward causality. Cause precedes effect. The billiard ball strikes the cue ball, and the cue ball moves. The past determines the future, but in retrocausal interpretations, the future can also influence the past. The boundary conditions of the universe, at both the beginning and the end of time, determine the present. The future is not just a result of the past is also a result of the future. This is not a fringe idea. It has been explored by serious physicists, including John Wheeler, Yakira Haranov, and Hugh Price. They argue that the mathematics of quantum mechanics does not forbid signals traveling backward in time. In fact, the math seems to invite it. Consider the famous double-slit experiment. We have discussed it before. A photon passes through two slits and interferes with itself, but if we place a detector at one slit, the interference disappears. The photon behaves like a particle. The act of observation collapses the wave function. Standard quantum mechanics says the collapse happens at the moment of observation, in the present. But retrocausal interpretations say something else. They say that the future observation reaches backward in time and determines which path the photon took. The decision to measure or not to measure, made at the end of the experiment, propagates backward and alters the photon's behavior at the beginning. This is not magic. It is a symmetry of the equations. Just as the Schrödinger equation allows us to calculate the future from the past, it also allows us to calculate the past from the future. The direction of time is not encoded in the equation. It is a boundary condition, an assumption we make. If we drop that assumption, if we allow the future and the past to communicate, then time becomes a loop, a circular conversation. The present is the result of a negotiation between the beginning and the end of the universe, a cosmic transaction. This brings us to the most radical figure in the story of quantum time, Richard Feynman. In 1948, Feynman was struggling to understand the behavior of electrons. He was trying to calculate how they interacted with light, a problem that had driven physicists mad for decades. And then, he had an idea, a profoundly strange idea. He imagined that an electron moving forward in time was the same as a positron, its antimatter counterpart, moving backward in time. Let me say that again. Feynman proposed that a particle of antimatter is literally a normal particle traveling backward through time. When an electron and a positron annihilate, they are not destroying each other. They are meeting at a point where the electron reverses its direction in time. It starts moving backward, and from our forward-moving perspective, it looks like a positron. This is not a metaphor. This is the mathematics of quantum electrodynamics, one of the most precisely tested theories in human history. Feynman's diagrams, those elegant scribbles of lines and loops, are maps of particles moving forward and backward in time. They are the blueprints of reality. Feynman once said, with typical irreverence, that the total number of particles in the universe might be one, just one, an electron, moving back and forth through time, appearing as billions of particles at billions of different moments. We see a forest of particles because we are trapped in a single slice of time. But from outside, from the frozen block, there is only one path, one world line, one eternal traveler. This is the first hint that time travel is not only possible, but ubiquitous. Every particle in your body is constantly interacting with particles moving backward in time. The future is already entangled with the past. The arrow of time is a local illusion. At the quantum level, the traffic flows in both directions. But can we exploit this? Can we send a asterisk message, asterisk backward? Can we, as conscious observers, reach into the past and change something? Not a particle's path, not a photon's behavior, but a macroscopic event, a memory, a choice. The answer, according to the physics we have uncovered so far, is both yes and no, and the distinction lies in the nature of information. In the 1980s, a physicist named Igor Novikov formulated what is now known as the Novikov self-consistency principle, asterisk. The principle states that if time travel is possible, then the probability of any event that would create a paradox is exactly zero. The universe is self-consistent. It will not allow you to kill your grandfather before your father is born, not because it is illegal or impossible, but because the laws of physics actively prevent it. Novikov imagined a billiard ball entering a wormhole, traveling back in time and emerging to hit its past self, deflecting it so that it never entered the wormhole in the first place. This is a paradox. The ball goes back, prevents itself from going back, so it never goes back, so it is not prevented. A logical loop. Novikov showed that the equations of physics allow only one solution. The ball can go back, but it cannot hit its past self in a way that creates a paradox. It might graze its past self, changing its trajectory slightly, but still causing it to enter the wormhole. The universe finds a consistent path. The past is not changed. It is preserved. It is smoothed over. But quantum mechanics offers a way around Novikov's restriction. In the classical world, a paradox is a contradiction. In the quantum world, a paradox is just a superposition. Let us explore the Deutsch model of quantum time travel *. David Deutsch, the physicist who pioneered quantum computing, took Novikov's ideas and applied them to quantum mechanics. He imagined a particle traveling backward in time through a closed time-like curve, a path in spacetime that loops back on itself. In classical physics, a closed time-like curve forces a single deterministic history. The particle must follow a specific path to avoid paradoxes. But in quantum mechanics, the particle is a wave function. It can exist in a superposition of histories. The particle enters the loop, travels back in time, interacts with its past self, and emerges. But instead of creating a paradox, the universe creates a quantum state, that is self-consistent. The math shows that such states exist. They are not paradoxical. They are just entangled. The particle leaving the loop is correlated with the particle entering the loop. The two versions of the particle coexist. The past is not changed. The past is branching asterisks. The time traveler does not enter a single history. They enter a superposition of histories. And emerges. But instead of creating a paradox, the universe creates a quantum state, that is self-consistent. The math shows that such states exist. They are not paradoxical. They are just entangled. The particle leaving the loop is correlated with the particle entering the loop. The two versions of the particle coexist. The past is not changed. The past is branching asterisks. The time traveler does not enter a single history. They enter a superposition of histories.